Bismillahirrahmanirrahim. In the last class, we had derived an expression for the general FEM equation that is applicable to all problems, all static equilibrium problems in stress analysis. Now, this is a very familiar expression, and the details that we derived last time came out to be like this. This is just a recap, and because we are going to use these expressions today, so it's a good idea if we write them down again. Here, this is the K of the system. This is for one element, and you repeat it for all the elements as mentioned here. And inside the element, you integrate it over the whole volume. As far as F is concerned, it was composed of different components. One was thermal strain vector, the temperature vector, temperature force vector, the body force vector, and the pressure load vector. And these were also calculated on an individual level, on an individual element level, and then they were again summed up for the whole system. And this is, we know this process, assembly, and this is done using the connectivity table. We are familiar with this process. And finally, there is a concentrated load vector, which is for the whole system. You do this process, and then at the end you add the concentrated load vector wherever there are forces, point loads. Now, what about the details? This F naught was, it came out to be again a volume integral. So we are talking about the element level integration. You do this, and then the body force vector, it was again a volume integral. So you do this integration for each element. And finally, the pressure load vector is a very similar expression, only this one is a surface integral. So you do, for each element, you calculate these, integrate these, and then you integrate this whole thing. This is for one element, then you make sure that you include all the other elements by this process, and right at the end you include the concentrated load vector if there is one. So these were the equations that we had derived last time, and we had left it at that. And we had only mentioned that these equations, because there are no assumptions here, we have not limited these expressions to 1D or 2D. So these are general expressions for all the problems. Now let's see what happens when we encounter a 1D problem or a 2D problem. So let's start, or a 3D problem for that matter. So let's start with 1D elasticity. Obviously, in 1D elasticity, these general expressions will take some concrete form applicable to 1D problems. So let's see what that form is. Now, if you consider these, there are some familiar things. You're familiar with D matrix, you're familiar with the B, you are familiar with the N matrix. I'll just recap. If you recall from one of the previous lectures, this B matrix is nothing but minus 1 over L and 1 over L for 1D case. And what is this B matrix? Just to remind you that this is just a link between the nodal displacements and the strain vector. Now for 1D, there's no need for these parentheses because this is not a vector at all for 1D. For 1D is a problem. A typical problem will be one element will be 1D element will be like this. It will have maybe there is a series of such elements, but if this is the x-axis, then the quantity of interest is simply epsilon x and sigma x. That's all. We are not concerned with the other direction stresses and strains. There are no stresses in the perpendicular direction. There are strains, but they can easily be found out using the Poisson ratio. So we are just dealing with this. So we can just write this simply as there's just one component of it. Similarly, when we talk about this D matrix, we know that generally the expression for Hooke's law is something like this, and if we subtract the effects of initial strain as we must, then this is the shape of the Hooke's law. But here again, this no need for these parentheses. This is not a vector at all. Here it is just a number, epsilon x. And this too, for 1D problems, you don't need a matrix of elastic constants. It's just one number will suffice. Similarly, these two are also numbers, simply numbers. There are no components in any of these quantities. And what about, I'm sorry, epsilon naught. And what about epsilon naught? Epsilon naught is a thermal strain. Thermal strain for 1D, we are familiar that this is the expression for it. So now we have all the ingredients for 1D that can be used here to tailor these general equations to our 1D problems. Let's start with K here. This is the I'm going to talk about the elemental integration only, because once this is done, this we know is done by connectivity table. We don't need any further development for that. So just putting in the values, because it's a transpose, so this D is simply E, and this is again. Now here, if our assumption is that it's a prismatic element, there's just a cross-sectional area A and a length L, and the A doesn't change, then A is a constant. In that case, we can write dV is equal to A dx. Now we have imposed a limitation here. The A is a constant. Will make our development easier, but again, if in future you get something like this kind of a problem in which A changes, then this limitation will mean that you will not be able to model this kind of a bar, tapered bar, by one element. You'll have to divide it into many different elements, and each element will, maybe you'll take the average of the middle point area. So this limitation will be there, but as long as the prismatic elements are concerned, this will give you the exact solution. So if we can change this into A dx, then this becomes a length integral, not a volume integral. And taking the constants out, E goes out, A is a constant, goes out. If you multiply these, this becomes L square, and if you open these, multiply these two vectors, you'll get 1 minus 1 minus 1 1, and all that remains inside the integral is this, and which is equal to length. If you simplify it, then simply this is your K matrix for 1D problem. Now this is again a familiar matrix. We had derived this for 1D elements earlier too, but at that time we were not able to deal with such vectors. It was a very simple affair with axial members and subjected to concentrated loads only. So at that time our development was very limited. Now because we are coming from the general equations, obviously we get the same result, which reinforces our knowledge, but the next results will be new for us, as well as the results for 2D and 3D. Now if we move on to our next vector, which comes out, which is the temperature effects. Whenever a 1D problem involves change of temperature, again just copying from our expression from what we have derived earlier, let's put in the values again. Minus is a transpose, so D is simply E, and epsilon naught, like we discussed, is simply, for 1D problem, is alpha delta T simply. And again dV, because the same, we have limited our treatment to a prismatic element, so one with a constant cross sectional area, it doesn't change, the area doesn't change, it's a constant, so we can express dV as a dx, and then it becomes a length integral. And if we take the constants out, E a alpha delta T over L, this also goes out, L, this minus 1 also goes out, and all we are left with is this, which is of course equal to length. There's an E, there's an A also here, so now this cancels with this, E a alpha delta T minus 1 is the vector, and this is for 1D again. The next one, body force vector. Again, very simply, it is actually, this is the general expression is this, but it's very obvious that it's a 1D problem. For a 1D problem, the body force has to pull this thing in this direction only, x-axis direction, because if it pulls this in this direction, displacements will be in this direction, so it will not be a 1D system to start with. So if it's a 1D system, the body force also has to act in the x direction only, although it will be acting on the whole body, but it will only act in the x direction. So the weight is out. Magnetic force can be there, but the weight is out. The only way a weight can be incorporated in a 1D problem is if it's like this. In that case, obviously, the pull of the earth will be in the direction, axial direction, but otherwise, and both these directions, this and this, these are the axial directions. So in that case, maybe we'll take the x-axis as this one. So which means actually that we can simply replace this by a number x only, because there's no concept of components of body force. The body force cannot act here or here. There's no combination. There's just one direction, and that direction has to be the axial direction. And it's very simple. If we extend this Ni and J, these are the because this is the transpose x, and again dV we can write as dx, and this becomes a length integral. Now x and a, they go out, and we are basically left with an integral of this quantity. Now, because we are familiar with the factorial formulas of integration, this is very easy for us. Please recall the factorial formula Ni dx, for example. This is your, so we were able to write this as L11 L20 dx, and this came out to be actually 1 factorial, 0 factorial, 1 plus 0 plus 1 factorial into length. Very simple for us. As long as the element is simplex, the integration is no problem. So this comes out to be actually L over 2. And this ni dx, this thing comes out to be L over 2. Then this thing also comes out to be L over 2. Please confirm this. Because it doesn't matter if the power is, if the L1 has power 1 or L2 has power 1, doesn't matter, the result will be the same. So if we put these values back, FP comes out to be actually XAL over 2, and there will be 1 and 1 because it's a vector. So again, this is your body force vector. Finally, let's take the pressure force or the surface distributed force. This was the expression. Here we had this surface integral, and similar to the body force, the pressure, the only two faces on which the pressure can act in a 1D problem is either this area or this area, either I node or J node. So let's suppose it acts on J. Now the only direction of pressure that is applicable again is Px. Py, Pz, that kind of thing will make this problem a 2D or a 3D problem. So we can just write this. If it's a 1D problem, then this is the expression for 1D only. And if we put in the values here, Px goes out, Ni, Nj, ds. Now it's very obvious. We don't need to integrate it at all, like we did here, because the body force was acting on the whole of this body. And what this vector tells you is, you apply a part of this force on I node, this part, and the other part on the J node. And if you consider this carefully, this AL is nothing but volume. So this Newton per cubic millimeter multiplied by volume, it will give you newtons. The force, the total force applied on this body due to the body force on this element, and then half of it is applied to this node and half to this node. But if we come to this, if we consider that P is only applied in this direction and on J node only, then this I node, this has this I node. What was the first property of shape functions? It was 1 at its own node and 0 at another node. So we are talking about this point. So Nj should be 1 and I should be 0. So it simply becomes Px 1, 0, and which is basically S, and S in this case is, let's say, this cross-sectional area, which means that we are talking about this, this should be 0, this should be 1, because we said it is acting on J node. This is 1, this is 0. Now it's very obvious that if we assume the opposite, force is acting here but not here, then the 0 and 1 will shift, and will also depend on the direction of the force. If it's in this direction, that will be positive, otherwise it will be negative. But I think you get that point. So this is for the case of for pressure at the J node. For I node, you can change this accordingly. It's obvious that this sort of pressure will only occur at the end. For example, if we have this sort of a system, let's say, most probably this kind of loading can only occur here, although it can also occur here, but and then in that case you will take the area accordingly. Outer area of the this bigger one minus area of this, because no surface pressure can act on this part. So you have the expressions for all these. If I write them together for in one place, this will turn out to be something like, for one element, using the expressions we have derived for all these matrices and vectors, we'll get something like AE over L. This is the K matrix, you can recognize this now, and this is some summation from first, this is for one element and this is for the whole system, and then you have UI UJ for 1D problems simplex. For one element there'll be just there'll be just two nodes, and you will be basically summing this all up. And on the right hand side there'll be E A alpha delta T minus 1 minus 1 minus 1 1. This one we just derived it, plus let's take this for pxa 0 1 plus take the B matrix FB xal over 2 1 1, and you sum them all up from the first element to the last element. So you all calculate these on an individual element basis and then sum them all up, and at the end you add the concentrated load vector. If you consider this expression again, this makes a lot of sense. This px will be in Newton per square millimeter, this area will be in square millimeter, so if you multiply them you'll get newtons, and then you apply all of it to the J node because it is acting on the J node. Here for B matrix, x will be in Newton per cubic millimeters, and this is volume cubic millimeter, so you again get newtons, force in newtons, and newtons, the force you divide by 2 and apply half to this and half to this. It makes sense. If the body force acts on the whole element, then half of it should go here, half of it should go here. Remember that for FEM there is no scope of applying the force anywhere in between. You can only apply the forces on the nodes. Actually they are applied on the whole body, but you apply them on the nodes. Similarly, if you look at this, if you put in the different units here, you should get a Newton, because on the right hand side you should have all the quantities having the same dimensions, and that is Newton or what, or kilonewton or whatever. So this is the expression for 1D elasticity. Now you should be sure that this is for px at J. If this px is of course at I node, then you'll have to switch these 0 and 1 like this. So that brings us to the end of the formulation for 1D elasticity. Now let's look at some problems, and that is the easier part. By far the easiest part is application of this. The hard work you have already done. For example, we take the first problem here. Let's say this 10 kilonewton force applied here, and the dimensions of this bar are 100 millimeter and 100 millimeter. A1, both have different cross sections. This is 20 square millimeter and this is 10 square millimeter. And this whole system, apart from this 10 kilonewton force, there is also a temperature change of delta T is equal to 50 degrees centigrade. So the temperature is increasing. The material is steel, and for steel, the Young's modulus is 200 GPa, and the coefficient of linear expansion is 12 into 10 raised to the minus 6 per degree centigrade. And you're supposed to analyze this. Now, analyze means you have to calculate the stresses. So in FEM, we'll start with displacements and then strains and then stresses. So let's start. It's very simple. We have to do this for all the elements. AE over L, 1, minus 1, minus 1, 1. This is our K. Now for the first element, we call this element number 1 and we call this element number 2. And because there are two cross sections, so our system will be something like this. We just need two elements, 1 and 2, and the nodes 1, 2 and 3. So for the first element, AE over L, we have to use the values. We'll use millimeters and newtons, and if we use millimeters and newton, then stresses that we are going to use should be in MPa, Newton per square millimeters. So we have to convert this into 200 into 10 raised to the 3. Now this is in MPa. Over L is 100. This is 1 minus 1 minus 1 1, and this comes out to be 4 minus 4 minus 4 4, 10 raised to the 4. Just write it outside to save time. Now K2. Now actually we should write, but you get the picture. In here, in any case, E's are the same for both, but still, if we want to be proper, then we should write it like this. In this case, L1 and L2 are equal, and so is E1 and E2, but in many problems they won't be equal, so should be careful about that. In this case, it is 200 into 10 raised to the 100. In this case, we get 2 minus 2 minus 2, 2, 10 raised to the 4 is outside. It's being multiplied by every quantity. Now this we have done. Let's do these also. F01, we're talking about the thermal, the temperature force vector. 200 into 10. For first one, area is 20. Alpha is the same for both, but it is 12 into 10 to the minus 6 into temperature 50 plus 50. You have to keep the sign in, keep track of the sign. If this is in negative, you put in negative, because negative has a different effect. It tends to contract the system. Now minus 1 1, and if you calculate the values, they come out to be minus 2400 and 2400. They'll be in newtons because we have used Newton per square millimeter. This is square millimeter, and this is dimensionless. This is with respect to temperature. This is not dimensionless. This is basically per degree centigrade, and this is in centigrade, so they cancel out. So basically, you get in newtons. F02, very similarly, because we are going to do it for two elements here, and then we'll assemble later on. So it comes out to be 10 into 12 into 10 raised to the minus 6 into 50 minus 1 1. So it should be half of this, again in newtons. Now in this system, FB is equal to 0, no body forces. fp for either for element 1 or element 2. Similarly, fp is also equal to 0. So actually, if I am accurate, I should write 0 0 because it's a vector, but you get the point. Now, was there had there been some pressure at this end or some body forces, we would have done the same procedure here, but they are not there. So we have the element level work done. Now we have to assemble them together. Now how do we do assembly? Please recall the connectivity table. Although for questions of this simplicity, obviously you don't actually need it, but I suggest that you make it anyway, because there are a lot of things that you do in your mind and you make some assumptions and then you make a mistake. So elements, no, it's always better to do things in writing. This is I node, this is J node. This is how we assembled a connectivity table. You're familiar with this. There are just two elements, element 1 and element 2. For element 1, the nodes are 1 and 2. For element 2, the nodes are 2 and 3. So how to do this process, this assembly? Very simple. There are 3 degrees of freedom for this system. You simply make 3 spaces here, 1 2 3, 1 2 3. Here will be u1 u2 u3, and on the right hand side should also make 1 2 3. Now this element 1 connectivity, node 1 and 2, so it should occupy these 2 spaces and also these 2 spaces. So it comes simply 4 minus 4 minus 4 4. Element 2, it occupies 2 and 3, so it occupies 2 3 and 2 3, this space. So here you'll superimpose minus 2 minus 2 2. Here you get zeros because there is nothing that comes in this space. How about forces? For forces you do the same. The first force should occupy, just write 1 2 1 2 2 3 2 3. Similarly 1 2, second one 2 3 1 2, minus 2400 2400, second place. Second one minus 1200 1200, so it takes superposition and 1200. So what you get as a result of this is, if we write it down again, 4 minus 4 0 minus 4 6 minus 2 0 minus 2 2 u1 u2 u3, and on the right hand side you get minus 2400 and 1200 and 1200. Now at this stage, when you have completed everything, you have completed this summation over all elements, you complete this summation over all elements. Now I recommend, and the equations tell you the same, now put in the concentrated load vector. Concentrated load vector acts on node number 3, so it is simply an addition of 0 0 and 10,000, because there's no summation involved here. It's just a vector and you just put in the values at the relevant places. So your final FEM equation will come out to be this. This is your final FEM equation. Now, we have already discussed different ways of checking whether it's true or false, true or erroneous. For example, you add them together, they are zeros. at this side all the rows and columns all add up to 0. It's symmetric, so there are good indications that it is all right. Now this also happens to be a singular matrix, so you are not able to solve this without applying the boundary conditions. There's no inverse of this matrix. So the boundary condition is very simple. There is one node which is fixed, u1, so we know that u1 is equal to 0. So if u1 is equal to 0, then it's very simply a matter of, if I just write it down again, this becomes 0, and for this to become 0, obviously there is a force supplied by the wall, and because of this force this becomes 0. But because this is 0, we are not this multiplies with all of these, so we can ignore these, and we already know this is 0, so we don't need this either. So all we need to do is take this, you just ignore this, your, and here obviously there is a, you cannot afford to forget this everywhere, otherwise you'll make a mistake just like I was about to. Now this is now solvable, this is invertible, we can solve this, and the answer is very obvious how you should solve this. To invert it, two goes there, 6, 2, 1200, 11,200, and this u2 and u3 turn out to be, if you calculate, 0.31 and 0.87. The answer will be in millimeters because we have kept that convention, newtons, millimeters, and newton per square millimeter, so the answer will always be in millimeters. Now if I write the complete u1, u2, u3 vector, 0, 0.31, 0.87. Now the rest is simply post processing. This is actually the FEM part is over here, so now we have to calculate the strains. The strains are nothing but B, recall, and B for minus 1 over 100, 1 over L, and 1 over L because L is the length. And for the first element it's simply this u1 and u2. For the second element, 1 over L and 1 over L will be the same because both have the same lengths, but here obviously second element, for the second elements the nodes are 2 and 3. The first element the nodes were 1 and 2, that is why in this case we have 0.31 and 0.87, and on calculation this comes out to be 3.1 into 10 raised to the power minus 4, and this comes out to be 5.6 into 10 raised to the power minus 3. This one is also minus 3. Now these are the strains, and just to stress this point here, these are the total strains, and this is a very significant point. This is the total strain. This strain is because on the right hand side we have this temperature and also the force. So this strain, these u's are as a result of both of these. This is the total strain. Now It's very tempting to jump to stresses here, but if you calculate the stresses from these strains, that will be an overestimation, because these have thermal effects incorporated and stresses have nothing to do with them. So here we again recall that for D, for sigmas in our case will be E and total minus. Now what about this? This was alpha delta T, which is 12 into 10 raised to a minus 6 into 50. Now this will be the same for both. It doesn't matter if it's 1 or 2. So the epsilon naught 1 is this and epsilon naught 2 is the same material, same delta T. So now the next step will be mechanical. Epsilon mechanical 1 will be epsilon total 1 minus epsilon thermal 1. And this turns out to be 2.5 into 10 raised to power minus 3. Mechanical strain in the second element, total strain in the second element 5.6 into 10 raised to power minus 3 minus thermal strain, and this one comes out to be 5 into 10 raised to power minus 3. Now we have these, so now it's very easy to calculate. Sigma 1 will be 200 into 10 raised to power 3 into 2.5 into 10 raised to power minus 3, which is 500 MPa. Sigma 2 epsilon 2, which is same as epsilon 1, but Young modulus 2, and into the strain 2, 200. This is the same, but this one is different, and this turns out to be 1000 MPa. Now these are our final answers. Now let's see if they're making sense. They should. This is a kind of problem we can check in so many ways. So if it's 10,000, what should be the stress here? The cross-sectional area is 20, so it should be 10,000 divided by 20 is 500 MPa. Sure enough, we have 500. Similarly, 10,000 divided by 10 should be 1000 MPa. As far as this delta T is concerned, that does nothing to stresses, nothing to do with stresses. Strains, yes, but when it comes to stresses, it is irrelevant. So that is the end of question 1. I think we should take a couple of more questions and maybe make 1 or 2 other points that we haven't made yet. What if we take the same question, exactly the same question, except there is no force. There is no force here. Nothing. The only thing that is there is delta T. Same 20 square millimeter, 10 square millimeter. This is the same 100 mm, and again 100 mm. Now the good news is more than half of the problem is already done, and the reason is that the K matrix doesn't depend on the loading. The K matrix, whether this load is here or not here, it doesn't matter. The K matrix If you calculate it, it will still be the same. It doesn't depend on the loading at all. It only depends on the materials and the dimensions. So we already have this K matrix with us, so that is the easier part. The other good news is we also have the temperature force vectors, and the result was this one, except this one. This part was the concentrated load part. Concentrated load. If we take this, this is our FEM equation for this question. Obviously, if there were other dimensions, different dimensions, we could have started from scratch too, but because these are the same, so we can just adapt these things. So now here, obviously, the boundary condition will still be the same. Like last time, the boundary condition will be the same. This one is 0, so this vanishes. So ultimately, you get something like and inverting it will still give you the same. This vector will be different, but others are the same. And if we calculate these values, they should turn out to be zero point 0.06, and the next value should turn out to be 0.12. Again, millimeters. There's no mistake about that one. Has to be in millimeters. Now, these are the values. Calculating the strains again, total strains, and obviously the complete U1, U2, U3 will be 0, 0.06 and 0.12. Now this will be minus 1 over 100, 1 over 100. This is the B matrix, 0 and 0.06, and this comes out to be 6 into 10 raised to the minus 4. Total is again minus 100, 1 over 100. B matrix doesn't change because the lengths are the same. Here you get the same difference, so you will get the same 6 into 10 raised to the minus 4. Now, before going to the stresses, obviously we need to find out the thermal part of it. We have to subtract the thermal strains from these total strains. And if you recall from the last example, and there's no reason the things should change here, the alpha delta T gave you 6 into 10 raised to the minus 4. And that is for 1, and epsilon naught for 2 also. It was 6 into 10 raised to the minus 4. So it turns out that all the strain in this problem is thermal strain, which is very obvious from here. There's no forces here. So there will be strains, but all of them will be thermal. So there will be no stresses. Why? Because obviously epsilon 1 mechanical becomes 0. This total minus thermal 0. Similarly, epsilon mechanical 2 is also 0. And when you calculate sigma 1 and sigma 2 using Young modulus, both become 0 as they should be. So this is the end of the second question, and I think we don't even need to check these because the stresses are 0 as they should be. Now probably there's some time for the last problem. We can add in one more. And let's take a problem. Let's make a new problem from these so that some of our work is saved again. Same dimensions. Everything is the same. Delta T is equal to 50 degrees centigrade. But now here there is a wall here at a distance of 0.1 millimeter. Now, because we have the benefit of hindsight, we have seen that the problem before this one without a wall, the sigma 3 was more than 0.1, 0.12. So it's more than 0.1. So if we didn't know that, then we had no other choice but to first do this problem without this wall and see whether u3 is less than 0.1 or not. If it's less than 0.1, then the wall doesn't play any role, so we can ignore it, and it was pretty much the question like we did last time. But if the sigma 3 is greater than 0.1, so it means it touches this, so this makes the question completely different. So in this case we know it touches, so what should we do? I think it's very obvious now in this case, because again there is no concentrated force here. There's no reason for the matrices to be any different than last time. The only difference in this case will be that of the boundary conditions. And what should be the boundary conditions? Obviously this line is irrelevant. u1 is 1, u1 is 0. We know it is 0. u3 is also known because u3 cannot be, and if this extends more than 0.1 without this wall, then this wall stops it here because it's a rigid wall. So we also know that this is 0.1. So the only equation of interest for us actually is the second equation. This minus 4 multiplies with u1, which is 0, so it doesn't count. So basically what we have here is 6 into u2 minus 2 into u3 is 0.1. We know this is equal to 1200 into 10 raised to a minus 4. I'm taking this power to the other side. And this comes out to be 0.0533. u2 comes out to be 0.0533 millimeters. Now if this is 0.0533, then r vector becomes, because the other two values we already knew, 0.0533 and this is 0.1. So let's do the remaining formalities. Epsilon 1 comes out to be minus 1 over 100, 1 over 100, 0.0533. Which is 5.33 into 10 raised to power minus 4. Similarly, epsilon 2 minus 100, 1 over 100. This is B matrix. I use the other values 0.0533 and zero point 0.1. Now this should turn out to be 4.67 into 10 raised to the power minus 4. These are the total strains. Now the thermal strains, alpha delta T, we know the same. We have been doing it for the last two questions. 6 into 10 raised to the power minus 4, epsilon 2 again, alpha delta T, 6 into 10 raised to the minus 4. Now epsilon 1 mechanical will be the difference between this and this one, which is minus 6.7 into 10 raised to the power minus 5. And let me check this again. Yes, that's true. And the mechanical strain 2 is 4.67 minus 10 raised to the power. Now all that needs to calculate is sigma 1. Now we are in a position to use the Young's modulus with similarly sigma 2. This is the Young's modulus, and this comes out to be minus 13.4 megapascals, and this one should be double of that. Sure enough, around about 26.7 ampere. How do I know this is double of that? Because at some point it would have touched it, and after that this wall, both walls would have pressed against these two. Now the force, because there are just 2 points of forces, so this kind of force enters here and leaves there, so the force is constant throughout. So just that force, whatever that force is, divided by this area will give you stress here, and divided by this area will give you stress here. This area is half of this area, so this is the end of your practice problems. Thank you very much.